Hello, everyone, and Happy New Year, and welcome back to yet another term of the online seminars. My name is Natcha, and I am here today with my colleagues Ji Kai. We are PhD students in architecture at Cambridge University, and we are the conveners of the Martin Center Research Seminars. For those of you who haven't been with us before, this research seminar is hosted and supported by the Martin Center for Architectural and Urban Studies. This is the research arm of the Department of Architecture at the University of Cambridge. Today, we welcome you to the first seminar of Lent term. This is the 51st annual series, and it is themed around the discussions on architecture and energy. For the past 50 years, these seminars have been held in Lecture Room 1 in Scroop Terrace, at which the Department of Architecture is located. Normally, we would welcome you to our department and offer you some hot beverages and biscuits. But due to the current circumstances, we virtually welcome you to our home. So this transition from an in-person seminar to the virtual one would have not been possible without the support from the members of staff and the student in the department. In particular, this wouldn't have been possible without the support from Dr. Ying Jin, director of the Martin Center, who is here with us today. So the advantage of us going virtual is that we have been able to reach a global audience. We have over 120 people registered for this talk and tuning in from all over the world. Now onto some quick housekeeping before we start. The talk is going to be about 40 minutes, and then we will open up the floor to questions. If you have any questions during the talk, please feel free to type them in the Q&A box, and we will read them out on your behalf. Or if you wait until the end, you could virtually raise your hands by clicking the button on your screen. We will then invite you to join the panel, and then you can switch on your video, your audio, and then you can talk to the speaker directly. This is obviously a lot more interactive, so if you could do that, that's preferred. The webinar is being recorded, but only for archival purposes, so please rest assured that you won't appear on the internet, so do feel free to ask away. Today, we are extremely honored to welcome Professor Phil Steadman, who had been one of the founding members of the Martin Center himself. I will now hand over to Ying, who will introduce you to our speaker.
I'm muted. Great. Thank you so much, Natcha. Congratulations to actually have pulled off a really good series in these really difficult circumstances, and continue to do well. So you and your colleague Jikai and many colleagues, I think, in the background still working with you as well. It's my great honor and a pleasure to introduce Professor Phil Steadman. Phil is a Emeritus Professor of Urban and Built Form Studies at University College London, or UCL, and the leading figure at the UCL's Energy Institute. Phil has been leading studies on the geometry of buildings and cities since the 1970s. In fact, at the time, he was at the Martin Center here in Cambridge, as Natcha says. I can still remember that the first book I read on the subject was written by Phil. I'm also aware that many students at the Martin Center today, including several PhD students of mine, are reading his works on the subject. And Phil would be pleased to hear that. Some students may even come and ask questions. In fact, they have already done so.
Very good.
In our own research work at Martin Center, we've greatly benefited not only the intellectual insights from his work, but also the data sets Phil has led to create over the years, for example, in his work on building form and building energy. Phil has kept close contact with the academic and research colleagues at Martin Center over these years, and it's great to welcome Phil back. In this talk, Phil has structured the presentation of his recent work under the title Energy, Density, and Built Form, 3 top keywords for this audience, I believe, and really much look forward to it, Phil. So I'll hand it over to you, Phil.
Thank you very much, Ying. Well, hello, everybody. It wouldn't be right to begin a talk on these topics without a talk indeed to the Martin Center, without a bow of recognition towards Leslie Martin and Lionel March. For younger members of the audience and people who are outside Cambridge, Sir Leslie Martin was Professor of Architecture from 1956 in Cambridge, and with Lionel March, he set up the Centre for Land Use and Built Form Studies, or LUBS, which was later absorbed into the Martin Centre. It got its rather unwieldy name from a study that Martin and March made in the late 1960s of the relationship between the forms of buildings and their densities. And if I can just share my screen, I'll show you the first slide, if I can find it. There we are. And let me see if I can, hold on. Here we go. Okay, so built forms. Lionel March defined them as mathematical or quasi-mathematical models used to represent buildings to any required degree of complexity in theoretical studies. And the work on density made use of three simple generic forms. Here they are. They called them pavilions at the top, the freestanding buildings, which when made tall would be towers, parallel streets, and then at the bottom courts, and you can see that this cruciform unit would, when repeated, make courtyards. And they imagined regular arrays of these forms continuing indefinitely. And they measured density as floor space index. So up at the top here, floor space index is the ratio of the total floor area of a building or buildings to the site area, the ground area. Later on, we'll use another index down below, the ground space index, which is the amount of the proportion of the ground that is covered by the footprint of the building. Martin and March made experiments by varying certain dimensions of these forms systematically while keeping others constant. So they kept the height of the stories constant and the depths of the forms in plan. And they also kept the cutoff angle or angle of obstruction constant. So the cutoff angle is the angle made by a line that joins the base of the facade of one building to the top of the facade opposite. And you can imagine that if you keep this angle constant, that as the buildings get taller, they're pushed further apart. And this graph shows the results. So on the y-axis, vertical axis, is density, floor space index, which they sometimes call built potential, but it's the same thing. And on the horizontal axis, the x-axis, the number of stories, the height. So look at the bottom curve here, curve for pavilions, freestanding pavilions or towers. And you'll see as the number of stories increases, density rises, one might expect. But after a certain point, it reaches a maximum and thereafter declines. Now, this is quite counterintuitive, where a lot of us are expecting that if we increase the heights of tall buildings, we make the densities greater. But Martin and March showed that under their assumptions, this was not the case, and I'll explain why. With the curves for streets and courts, the density rises continuously with height, and it levels off to a maximum in each case. Lionel March expressed two theorems on the basis of this work. Theorem one, I can't actually see the whole of my text. Oh, yes, we will. Comparing infinite arrays of rectangular built forms controlled by a given angle of obstruction, the floor space index of an array of continuous courts is always greater than that of an array of streets, which in turn is always greater than that of an array of pavilions for any given number of stories. So whatever the height is, if the three forms are the same height, the courts are always giving a higher density than the streets, and the streets are giving higher density than the pavilions. We had a second theorem. There is a maximum floor space index for an array of pavilions for some finite number of stories, and I've shown this with the red line. And for this same number of stories, the indices for streets and continuous court arrays are 2 and 3 times the maximum achievable by the pavilion array. So at this particular height, when the density of the pavilions reaches a maximum, the density of the built forms are in the ratio 3 to 2 to 1. Now, I'm not going to try and explain in detail why these results occur, but in very rough qualitative terms, they have to do with 2 effects. One is that the different built forms come to cover different fractions of the land area. The towers become less dense with height because the fixed cutoff angle is pushing the forms apart and is using more and more land, and the rate of increase in the land is faster than the rate of increase in floor area. That's why this effect occurs. And the second effect is to do with the way in which the forms look inward or outwards. So if you look at the bottom here, the courts, if you imagine the facades, the 4 facades of the court looking inwards, they are all using that piece of land to derive their air and light, so to speak. They're using the land 4 times. Whereas in the middle with the streets, the land between the forms is being used twice. And at the top, the pavilions, this is where the argument gets a bit hairy. Doesn't really work. But anyway, in principle, the pavilions, the land is again being used twice, but there is land that is not being used. Now, March made all these calculations algebraically by hand. Computers weren't used, and that was one reason for keeping the forms very simple. This is the early 70s. March recognized that there were many simplifications involved, and that more realistic and complex models could be devised. And one major simplification involved this cutoff angle. And the implication of the work was that if you kept the cutoff angle constant, then there would be an equivalent level of light, natural light, to the different forms. But that implied in turn that light only arrives at right angles to the buildings, which is obviously not the case. Light arrives in all directions from the whole part of the sky. So the bottom stories of court buildings are not as well lit as the bottom stories of tower buildings, because the courts, the view is obstructed by the sides of the courts, the opposite side of the court. Carlo Ratty, who was now at MIT, he did a PhD at Cambridge, and he studied this problem using lighting simulation software. And this is from his thesis in 2001. And the top left is the towers, the top in the middle, the streets, the middle in the bottom rows, sorry, the bottom right is courts. And he made experiments and adjusted the built forms such that the simulated level of natural light was the same in the bottom of the courts as it was at the foot of the towers. And that meant that Martin and March's results were not quite as extreme as they had calculated, but they still stood in terms of the order of priority in which the density increases. Density is still greater in courts than in streets, and greater in streets than in towers, pavilions. In case you're thinking that all these mathematical calculations are so abstract as to bear little relation to the real built environment, let me show you some measurements on actual buildings. These March and Martin's experiments might seem highly theoretical, but they serve to capture what generic qualities of what one might call toweriness and streetiness and courtiness in real urban developments. What I'm going to do is to show you photographs of a series of buildings or groups of buildings, most of them in London. And in every case, the floor space index is 3. The density is exactly the same. What changes is the number of stories and the built forms. So here we go. This is the old Bon Marché supermarket in Brixton, and it's almost solid. It's got a few little courts. It's on an average of 3.5 stories. The ground coverage is 0.6. 60% of the land area is covered. And I should explain that this includes, the land area calculates half the width of the roads around the block. Next one, just off St. James's Square, nearly 6 stories. Remember that the density is the same. The ground coverage is now 50%. This illustration shows what high densities were achieved in the 19th century in the centers of European cities before high-rise construction and elevators. Student housing in Leicester, a courtyard, 7 stories. Now 40% of the ground is covered, and the density is still the same. A couple of slabs in Bermondsey, 7.5 stories, 40% of ground coverage. Something approaching a tower in Farringdon, nearly 9 stories, ground coverage of 1/3. A big mansion block in Kensington, nearly 10 stories, again 30%. And the last example, what we're looking at here is the tower on the left and the slab on the right, not the curvy orange building beyond, but these 2 buildings in front, with an average of 14 stories, tower and a slab, 20% of the ground is covered. So you see what we've had in this sequence is exactly the same density achieved by a sequence of buildings that go from courts through slab-like buildings to towers. This is empirically the same as here Martin and March's theoretical predictions in practice. I'll tell you later how these detailed measurements of density and land coverage were made. My colleague Graciela Moreno and I have made the same point, illustrated the same points with a couple of recent schemes in London. On the left, sorry, yes, this is Foster and Partners, a scheme now completed for 250 City Road. 2 towers of 36 and 41 stories, plus some 7-story blocks. And on the right, we've taken exactly the same site and put exactly the same floor area in a courtyard on 8 stories. This is not obviously an architectural proposal, it's just a geometrical demonstration. Clearly many other factors besides density would come need to be considered. Here's a second example, very controversial scheme just on site in Swiss Cottage in London by Grid Architects, 24-story residential tower, blocks on 5 and 7 stories. And again, we've put all the same floor area on the same site in a branching slab on 11 stories, halved the height. Before leaving land use and built form studies in Cambridge, let me introduce my third topic, which is energy use, with a nod towards my old friend and colleague Dean Hawkes. In the early 1970s, Dean Hawkes and Richard Stibbs developed some of the world's first software for modeling heat flow and energy use in buildings. And here are some results for a series of built forms, again, March built forms. These are 4 rectangular blocks, which are on different numbers of stories, but have the same total floor area. And on the right, these are results from a simulation of cooling loads in summer. And as you can see, the cooling loads increase from 2 stories to 10 stories, because the areas of facade that are facing the sun are increased in area. And you could perhaps see at the top, there are 2 curves for 10 stories, depending which way the block is facing. Lionel March, by the way, looked at insulation of walls and roofs and asked what shape should a building be to reduce heat losses. And here's his optimized forms. In this case, 3 different results for optimization, depending on whether the forms are daylit or are artificially lit or have some combination of the 2. Now let's jump forwards 40 years to this century. Now the laws of geometry and the laws of physics have remained just the same. And to that extent, the work of land use and built form studies is still valid. But what has changed very drastically over this period, obviously, in our field and many others, the power of models to represent built form, density and energy use at the building and urban scales in ways that would have seemed quite fantastical and dreamlike in the days of Loves. It's worth emphasizing that in the 1960s, when I was an undergraduate, there was just one computer serving the whole of Cambridge University, the Titan machine. And Titan, despite its name, had the power and memory of a typical pocket calculator of the 1980s. I've been working on energy use in buildings since the 1980s with pocket calculators and computers. And I'm now, as Ying said, at the Energy Institute in UCL. And over the last 10 years, we've been developing a method for modeling energy use in the building stock at scale, which we've called 3D stock. And the main software architect is Steve Evans, my colleague. Other close colleagues are Rob Lilliard and Daniel Goddard. 3D stock is a tool to support policy and practice, but it's also a laboratory for studying relationships of energy and density and built form. Now, the 3D stock method is complex, so I'll just give you a sketch. It uses, it's completely automated, and it uses a large number of available public data sources. And the models cover all buildings in a region or city, domestic, non-domestic, and mixed use. The footprints of buildings and their addresses come from the Ordnance Survey, at the bottom here. The geometry of the external envelopes of buildings is calculated with LiDAR, laser measurements from the Environment Agency made from overflying aircraft, which calculate the heights of features on the ground and roof heights. In the absence of other information, we calculate floor areas by taking these volumes constructed from the LiDAR and slicing them. We assume a story height, we slice them at each story level so that in this semi-detached house here, we can calculate the floor areas of each floor level, including these extensions at the back. For non-domestic activities, we use commercial rating data from the valuation office, which give detailed measurements floor by floor and also classify activities in some detail, hairdressers, leisure centers, wine bars, and so on. And we've got information on the structure and materials of buildings from a commercial database called UK Buildings. We put particular emphasis on the relationship between premises and buildings, which is especially important in the non-domestic stock. Premises is an extent of floor area with a single occupier or tenant. And it might constitute part of one building, for instance, an office suite in a multi-tenant office building, or it might correspond to a whole building like a church or a small school, or it might be made up of a group of buildings on a shared site like a factory or a college. So in the domestic stock, we represent the relationship of flats to the blocks or converted houses to which they belong. And there are also many buildings in the centers of older cities in which domestic and non-domestic uses are combined. So here's a sequence, examples of mid-terrace former houses, some of which are still houses, many of them. In London, there's several million. We might have on the left an office occupying an old house, or offices over shops on the right, 20,000 of those. The building might have flats over combinations of shops, many of those. Finally, the whole house might be divided into flats. So we take account of all these. In academic work and in government policy, mixed-use buildings have tended to be overlooked because of their complexity and because there's been a kind of professional divide between the people who work on domestic and people who work on non-domestic, and these mixed buildings fall down the middle. The relationship of premises to buildings becomes particularly important when it comes to attaching energy data. So we use display energy certificates, DECs, and energy performance certificates, EPCs. The DECs give actual consumption, the EPCs give model consumption. Both can relate either to premises or to buildings. And in all cases, in order to measure energy intensity, it's very important to know which floor areas, which premises these certificates relate to. In the Building Stock Lab, we've done a lot of work for BEIS, the Department of Business and Energy. And they have let us have, under very strict constraints of confidentiality, access to actual electricity and gas meter consumption. And we've matched those into the 3D stock models by their addresses. So here's some examples the kind of complications that can arise. So that at the top right, a block of flats, or perhaps a block of office premises, there might be separate electricity meters for the separate premises, and then a gas central heating system for the whole block, or an air conditioning system metered separately. Bottom right, a school with many buildings. You might have some meters in the main building, and then perhaps other buildings without meters or with separate electricity meters. And then on the left, various complications that can arise in single houses and houses broken into flats. Bayes has a model of energy use in the building stock called need, which has no geometrical or physical representations of buildings, consists just of a list of addresses of dwellings and premises, to which energy meter data are attached. But because they don't take the relationship of premises to buildings into account, the rate of successful matching of the meters is low. It's about 50%. Whereas in 3D stock, we can manage to match 95% of the meters or more. So we've built, so far as built form is concerned, then 3D stock provides digital models of the envelopes of buildings, their floor levels. The area of external walls can be calculated. We can work out the adjacencies of buildings from their footprints, so we know whether they're detached or semi-detached and terraced and so on. The area of party walls and roofs are known, so we can then make calculations of the areas of the surface through which heat is lost. And all this can be done for very large numbers of buildings. And we've built models of Leicester and Swindon and Milton Keynes. And we've built a 3D stock model of the whole of Greater London for the GLA, which covers 1.5 million houses and nearly 2 million flats and 250,000 non-domestic premises. So here's some pictures. This is central London. The yellow outlines are boroughs of Westminster and the city, and the colours code for domestic and non-domestic and mixtures in between. So the bright red are non-domestic, pure non-domestic, and the dark blue are houses, the lighter blue are flats. This is the river snaking along here. This is the O2 Millennium Dome here. Go in a bit, same view, same colouring. This is the city. This is showing office buildings in this, beg your pardon, this is showing non-domestic buildings in the city. Now you can see some of the three-dimensional modelling that's capable, that LiDAR is capable of doing. This is St. Paul's. Here's the Tower of London down at the bottom. Here's the same view, but now these are display energy certificates and energy performance certificates attached. The colours code for, well, red is, G is bad, green is good, colours in between. Even Blackfriars Bridge seems to have a energy performance certificate, which is slightly surprising. And here's a view on Euston Road in the foreground, University College Hospital. And here you can see the floor levels. And again, the colours are coding for energy performance certificates. Now I said that a 3D stock model is a laboratory for studying energy use and density and built form and how they're related. But it's a laboratory whose tools are of a very different kind, those available in land use and built form studies. We don't have to represent the building stock with a few supposedly representative archetypal forms. We have detailed measurements on millions of actual buildings. We don't have to draw samples. We have what is in effect 100% sample. And we don't have to rely on energy simulation because we've got actual consumption, metered consumption for the great majority of the buildings. And at the Energy Institute, we've been promoting what we've called an energy epidemiology, by analogy with epidemiology in health studies, so that by analyzing variations in energy use against a series of background variables in very large populations, we can see small statistical effects, which it would be difficult to observe by small samples or by simulation. Let me show you some examples of work we've been doing. A couple of years ago, before the London model was fully complete, we examined the use of gas and electricity in houses and flats in 15 London boroughs, plus some of the other towns which we've modeled. And they amount to some just over 1 million domestic buildings, houses and blocks of flats. On the left, this is work by Donald Mitchell and Tony Hargreaves, who's here at Cambridge, on the relationship of residential density to dwelling type. And they measured a fairly large sample, and they expressed density here, not as floor space index, but as dwellings per hectare. So density is on the x-axis, and on the y-axis is the percentage of the total stock that is of that type, of that particular density. So if we move from the left, if I can find my cursor, move from the left, at the lowest densities, as one might expect, there are detached houses. And as density increases, these are progressively replaced by semi-detached, and then by terraced. And as we get to densities of 150 or 200 dwellings per hectare, almost all the stock is in flats. So on the right, this is our analysis of these 1 million houses with 3D stock models. And we see the same kinds of effects. Again, density, dwellings per hectare on this x-axis, percentages on the y-axis. The red is the detached houses, the yellow are the semi-detached, being replaced by green, the terraces, as density increases. Here we've split flats into smaller blocks, perhaps converted houses. They're in the blue. Purpose-built, these are in the purple. And we've also shown what is labeled here, the gray, as a measure of compactness, and that's perhaps misnamed, actually. What we've done is we've calculated the actual exposed surface area of each building compared with the surface area of 5 surfaces of a cube, assuming that heat is not lost through the 6th face of the ground. Our interest is in energy. So that a detached building that is perfectly cube-shaped would have let's call it exposure, an exposure of 1. But as what we see here is an increase in the relative amounts of a drop in the amount of exposed surface area in relation to party wall. So this measure is increasing. Kern Stamers, again, Cambridge colleague, illustrated the same kind of idea with a theoretical analysis here. What he's measuring is fabric heat loss by simulation or by calculation against the ratio of the area of the envelope to the floor area. This is exposed envelope in this case. And again, the highest is in the detached and so the bungalows, the lowest in the flats. Here are the results from our analysis of the metadata. Density increasing, dwellings per hectare on the x-axis. And the gas is blue and electricity is red. And you'll see that there's not much variation in electricity with density. This is dwellings, the greatest variation is in gas, gas being the main fuel, of course, used for heating this country. And it drops, as one might expect, because of this decrease in exposed surface area, decrease in heat loss over this range of up to about 300 dwellings per hectare. Interestingly, beyond 300, it starts to rise again. We have to be slightly careful because the numbers here are small and there are technical reasons why these results might not be entirely reliable, but interestingly, it starts to rise. I'll come back to that issue. We've looked at, my colleague Daniel Goddard and I have looked at the relationship of height to energy use in a sample of offices. Daniel's another link to Cambridge. He's working on a thesis, PhD thesis at Cambridge. We got together a sample of 600 office buildings in Britain for which we were able to get actual energy use, electricity, gas and oil. And their heights ranged from 1 story to more than 30 stories. Some were government offices, others commercial offices. Their ages ranged from the 19th century to the present. Some were air-conditioned, some mechanically ventilated, some naturally ventilated. And this graph summarizes our findings, so that height is shown on the x-axis in a group of, in ranges, 6 stories and below, 6 to 10 stories, 11 to 15 stories, 16 to 20, and 20 stories and above. And look at the colored bars. Blue represents electricity. This is kilowatt hours per square meter. So this is energy intensity. Electricity is blue, fossil fuels are orange. And as you can see, going from 6 stories to above 20, intensity of fossil fuel use increases by 40%, intensity of electricity use by nearly 140%. The black bars represent carbon emissions, and they are doubled. We didn't expect an effect of this magnitude. We expected some effect, but nothing on this kind of scale. There's a doubling of energy intensity with increase in height to 20 stories. Other people in the professions, I don't think expected this. They had been calculating energy use with height using simulation models and have not found this kind of result for whatever reason. Now, some of you, this is again one of the arguments I would propose for using actual energy consumption figures. Now, some of you might be thinking, well, these tall buildings are air conditioned and the lower buildings are not. And that's the reason. Well, it's not. Here we've separated the sample into air-conditioned buildings on the left and not air-conditioned, so mechanically ventilated, naturally ventilated on the right. And the numbers are roughly equal, 350 and 260. Should be a bit careful of these numbers in the smallest, in the tallest groups, particularly this one here. There's only 3 buildings. But otherwise, the air-conditioned buildings do indeed use more energy in every height range than the non-air-conditioned, but there is an increase of comparable magnitude in both cases. I was surprised to find so many tall buildings in Britain without air conditioning. It seems to be accepted wisdom in the industry that air conditioning is essential, but almost all skyscrapers built before the 1940s, of course, didn't have air conditioning. The Empire State Building still has openable windows. So what's the cause? It needs more research. There is not much data that breaks down energy use by end users in tall buildings. There is a study of tall offices in Hong Kong showing that lifts and escalators account for typically just 3% of all energy use, so that's not the reason. One might expect, there's no reason for expecting use of electricity for information technology to change with height. You might expect some change with lighting, but that would be perhaps to decrease the lighting load as buildings become taller and more exposed to the light, to the sunshine in the sky. My intuition is that it has something to do with the external environments of tall buildings and how these change with altitude. Air temperature decreases with height above ground. Wind speed increases with height above ground, as we know when we go to tops of tall buildings, tops of hills. In particular, it increases above the typical level of the roofscape, which in a city like London is 5 or 6 stories, 18 meters. And in summer, of course, taller buildings are exposed to greater solar gains. And we saw that effect predicted way back in the 1970s by Dean Hawkes in his computer calculations. One trend that we found in tall buildings, which you won't be surprised, was a greater prevalence of curtain wall construction in the taller the buildings become. There are some obvious implications here for planning and energy policy. The popular wisdom persists, as I said before, despite Martin and March, that tall buildings are necessary to achieve high densities. Sometimes argued that by building at high densities around transport hubs, residents can be encouraged to travel by public transport rather than private car, which is a good argument, but notice that it's a case for high densities, not for tall buildings as such. One issue for planning is that to build low or medium rise, high density courtyard developments, one tends to need larger sites. But if legal limits were to be placed on the heights of buildings, as they are in many American cities, for instance, then developers would have incentives to find larger sites in order to achieve high densities. How are we doing for time? I've got a bit of time yet. Going back to form and density, March and Martin made their studies by theoretical analysis of simple built forms. In the early 2000s, two researchers at the Technical University Delft, Mette Berghouser-Pont and Per Haupt, began measuring densities empirically in a large number of housing developments in Holland. And they devised an ingenious graphical tool which they called Spacemate. Here it is. It's a 2D graph. And on the vertical axis, the y-axis, they measure density as floor space index. And on the y-axis, ground coverage as a fraction, so that a ground coverage of 0.5 would mean that half the ground is covered by the footprints of buildings. And the relationship of ground coverage to floor space index is such that you can express numbers of stories by these diagonal lines that pass through the origin. So from 1 story down here, 2, 3, 4, 5, up to 13 in this case. And on the line for 1 story, we've got a ground, half the ground is covered, and that means that the floor space index is 0.5. The values are the same. This is, they express the same thing at 1 story. Berghouser-Pont and Haupt were motivated to carry out this kind of work by the realization, like Martin and March 40 years earlier, that floor space index on its own is not a very informative, not a completely informative measure, and many different kinds of development can have the same FSI. So I was showing you earlier with the photographs, and this is 4 of their photographs of Dutch housing developments on 2 and 3 and 5 and 11 stories. They've all got a floor space index of 0.7, and you can see the differences in kinds of form and the kind of ground coverage in those 4 cases. So Berghouser-Pont and Per Haupt plotted large numbers of measurements made with geographical information systems onto this diagram. And I have to translate their kind of terms. Down, they showed that they fell into these areas, zones within the Spacemate space. You found characteristic forms in characteristic locations. So down here, they define them with these ellipses. So these are what they call strips, what we would call terraces, and Martin March call streets. On 2 and 3 stories, low rise, and they're covering different amounts of ground. So they've got densities, floor space index, from going up to 1 maximum. All of these are what they're called blocks, and they mean courts. And these are courts on different numbers of stories, going up from 3 to 8, and different different cutoff angles, different building depths, and so on, which they call spacious and compact. And those, as you see, have densities go up, these are courtyard developments reaching floor space index values of 3, very high. Over here is a group they call high rise. These are point blocks and slabs going up to 30, from say 8 to 13 stories, averaging a density of 1, comparable with the most dense streets, terraces. So here are Martin and March's results, discovered again empirically. In our latest paper from the Building Stock Laboratory, which is in press at the moment, we've been using the Spacemate tool to plot very large numbers of buildings from our London model. And using the electricity and gas meter data, we've looked at how energy use relates to these Spacemate variables of floor space index and ground coverage. And we've measured these variables at different scales, from left to right, the progressively larger scales for individual buildings and their sites, grouped up into urban blocks, grouped into census output areas and the larger census output areas, going up to boroughs and to the whole city. And the land areas are measured using Ordnance Survey and land register boundaries, as I mentioned. For some of the calculations, we've taken the whole stock, but others with the energy analyses are confined to dwellings heated by gas. So for the dwellings, we have a sample of nearly 500,000. And this Spacemate plot shows them all. And it's not all that informative because there are, I say, 500,000 points, and on some of the positions there are many, many values superimposed. But you can see that the large part of the stock does not exceed 6 stories, as one might expect. Not everything lies on these lines of integral numbers of stories, and that's because, as we saw earlier, we represent back extensions and setbacks so that there are fractional numbers of stories. And we've highlighted 4 buildings here, 4 developments. So one is some 2-story houses, terrace houses. 2 is 3-story flats. 3 is a 12-story tower over on the left, and 4 is 5-story courts. And when I showed you photographs, a sequence of photographs earlier, those were measured by the same methods as we're using here. These plots show the entire stock, domestic and non-domestic, for these different spatial units, going from boroughs at top left to individual buildings and sites at bottom right. And of course, as one takes larger units, one gets averages, the numbers are smaller. Here, green represents one case and 10 represents a lot of cases. But you can see the concentration with these red values along 2-story line. Large proportion of the London stock is 2-story. And this is the same data, but presented as graphs. The proportion of the stock, the percentage on the y-axis, and number of stories, peaking around 2, as we see here on the left. Floor space index, the colors code for these different spatial units. And this little point here is the City of London, the red of boroughs, which has extremely high densities overall, extremely high density of that borough, very large numbers of tall buildings. And ground space index on the right. This is breaking the sample by the domestic sample by these detached, semi-detached terraces and flats. I like this graph. This is a graph of age of the stock. And here the colors code for the red is the oldest, the early Victorian, down to the dark green, which is the after 2000. And it's a kind of thumbnail history of the development of the building stock of London. So in the middle here, the red, this is the 18th century, 19th century terraces and squares of central London, quite high densities, going up to 6 stories. This orange area is broadly the kinds of by-law terrace houses built in very large numbers in the second half of the 19th century, 2 and 3 stories. This area of yellow down here, these are detached and semi-detached houses built in very large numbers in the suburbs as they grew in the period between the world wars. And then after the Second World War, with tower cranes introduced, I think, into London by Leslie Martin, if I'm right, buildings, high-rise buildings over 6 stories, and some very high density infill on this right-hand side. Finally, let's look at energy. So this is median energy use intensity, kilowatt hours per square meter, in the London domestic stock. And again, set on Spacemate. And look at the right, the electricity. Again, green is low and red is high. And electricity use is not strongly related to density, as we saw before. But on the left, gas use, we see how there is an increase in energy intensity signaled by this change from green to red with density and with the transition from looking the other way from detached, semi-detached through terraced to flats. So it's the same result presented again. And here the same results presented as graphs. On this one on the left, electricity is flat, gas is declining. Again, the compactness figure as we saw before. Now, what we've got new here, compared with the figures I showed you of the previous study, was densities of high densities, in this case above FSI of 3. And you'll see that the gas curve again begins to go up. And on the right, this is numbers of stories, and you'll average height on the x-axis. And you'll see that there is we have to be careful with these results. There are technical reasons why they're not entirely reliable, but it does suggest that there is an increase in energy intensity with height in residential of the same kind as we saw in offices, for perhaps the same kind of reasons. I haven't said much about practical applications of our 3D stock model, but you can imagine that they can provide the means with which to plan programs of energy improvements, retrofits towards zero carbon. And that's the main purpose of the model that we've built for the GLA. We're now working on several London boroughs on their retrofit strategies. The broad findings from much of this work with 3D stock Spacemate are not too surprising. They confirm things that we suspected, perhaps not in the case of the tall buildings, but otherwise what one might imagine a priori from previous work. The theoretical experiments of Martin and March are brought together with these empirical findings of the Spacemate tool. But I hope you'll agree that this work provides a picture of unprecedented detail in which a whole series of parameters, built form type, energy use, density, ground coverage, number of stories, are related together for millions of buildings. Thank you very much.